and he will tell us about precise reasoning with structured time, structured heaps, and collective operations.
Okay, can everybody hear me?
Yeah.
So thanks for the introduction. So that work was made in collaboration with my coworker Guannan and my advisor Tiark, so from Purdue University. So our goal is to improve the precision of static analysis for low-level imperative programs that have dynamic allocation. So such programs that have lists, trees, or graph. So let's take a very simple such program, which is a program that's going to build a linked list in a first loop, and then in a second loop, go through that list and do a reduction operation, and have some kind of assert at the end of the program. So such program is actually quite difficult for a static analyzer to verify, and let's see why. So we are going to execute the program in a concrete way first. So the first few steps, we have a local variable, and then when we enter the first loop, we are going to start to allocate a new node to that list. So this node is the first one to be allocated, so it's at the end of the list. It points to null. Then the head of the list is going to be the result of a function call. That function call may add a new value on the list, on the heap, and when it comes back, we set the heap, and so on. So we have done that first iteration, and then we go to the next iteration, and we allocate a new pointer, and now this list node is going to point to the previously allocated node, right? The pointer P1 that we had in the first iteration, and so on. We go to our function f and so on. And if we continue our loop iteration, at the end we have our full linked list. And in order to analyze this program, we are going to want to make a summary of the heap, trying to make a kind of a representation for the heap in order to reason about it. So we can start to reason by each point in the program that allocates something on the heap. We are going to make a modelization for the object that was allocated. So for our first seat allocation A, we know that it has a head and a tail, and the head is something that is a result of a function, right? But we don't really have more information. For the tail now, we have many possible targets, right? So each node that were allocated during the loop is a possible target for the tail. So it's kind of self-referencing, right? The node that we are allocating is self-referencing. But here, even if we are in the very simplest possible situation for dynamic allocation, we could imagine something a little bit more complex than start to have multiple allocation sites and have self-referencing between each other. It can very fastly become everything point to everything if we lose a little bit of precision in the process. And so what we realize is that we are losing information because the representation of the store is too low level. We lost the information of the time that at each iteration in the loop, we had a new allocation. And we see the store as a flat array, rather than we claim that we should see it as a structure heap, right? The heap was built following the structure program, and in the while loop, for example, it's like we allocate a new array at each iteration. So our solution is to introduce index I, and so now we know that at the location A, at the time I, we actually call the function f with the value I. So now we have a little bit more precise value for the head. And now for the head, for the tail, sorry, we know that at iteration I, we are pointing to the iteration I minus 1. So if it was the first iteration, we would point to null. Otherwise, we would point to the previous allocated node. So we can have a concise representation which is structured and as a collective form. So we thought about how to instantiate this idea, and so our solution is to take an imperative language, to translate it into a functional language which is semantically equivalent, and then simplify the functional language. So we could also apply other kind of transformation instead of semantic preserving, but we went for the most difficult case and we are going to see that we still have a good result. And of course, we cannot simplify a program ad hoc like that, so we are also going to introduce speculative rewriting that are going to interleave speculation with transformation, and we are going to see that later. So let's take the program that we had and apply the transformation. So the goal is to have the value of x, y, and I after the first loop. And for that, we are going to try to represent to have a functional representation for x, y, and I. And so at the end of the loop, we know that the value will be x applied to a given number of iterations. So in order to figure out that number of iterations, we have a constructor that is going to give us how many times the loop actually has been executed. And the value of x, y, and I are going to be given by applying the function to the given index. So in order to, we are going to translate that imperative language into a functional language. So for x and y, they are actually modifying the store. So there is an extra variable which is going to represent the heap. And so x is, if the loop has been executed, it's going to be the pointer that was allocated at context ctx at iteration j. And we see that here we give a special point, ctx, and a temporal j, which give us a unique spatio-temporal label for each pointer allocated at each loop iteration. And for the store, we see that we are creating a new object that has two fields, tail and head, and we update the store at index j. So we can also more simply represent I was the value of I at the previous iteration plus 1. And so now that we have our functional representation, we want to simplify it. So let's start by the simple one. So every time we have a loop, we are going to add 1 to the value. So it can be represented as a sum between 0 and j of 1. And that is simply, well, if j was greater than 0, then it's going to be j plus 1, otherwise it's going to be 0. Now if we look at the store is like, well, the previous store, and at index j, we are going to update with a new object. And so that can be represented as a collection, a new array that at each index, we are going to have the head of value that index. And for the tail, if it was index 0, then it was null. Otherwise, it was the previous object in the array. Now that we have a value for I, we can actually figure out how many iteration has been executed in the loop. So we can replace I by actually j. And so k is actually, if n was positive, the loop has been executed at time. Otherwise, it was not executed at all. And through some simplification step, we can have the value for I, and the same for x and y and store. So now we have the store at the end of the first loop. And we are going to do the second loop a little bit faster, but what is interesting is that now we have to dereference the store. We have to dereference the value pointer. So the sigma extract from the store the value of z. And so here it's not really interesting, but we are going to go through the list in reverse order. And because of that representation of z that is still precise, we know that if we different z of g minus 1 head, it's going to be equal to n minus 1 minus g by just doing a lookup into the store value that we had, we still had above. And that can, similarly with I we had before, can be transformed into a sum, and that is a well-known formula for an integer number. Instead of going from 0 to 1, is going to n minus 1, we go from n minus 1 to 0. And so at the end of the loop, we have our store. And so now we are going to look at the formal definition of our approach. So we start from an imperative language that is like a very generic imperative language that have dynamic allocation and can have possible error at runtime, so such as index out of bound or such a thing. And here is a big step semantic for that language. So there is nothing very interesting compared to any other language, but one rules that we would like to focus on is the while loop. So instead of having a while loop that executes each condition and body, we actually have an external judgment that's going to execute the loop body and the condition n time. And so while it's not very interesting if we want to implement that language, it gives us a hint that we actually want to replace a loop by a kind of a collection form with a parameter n, right? Like an array of size n or something like that. And so we just have to guess the n for the rule. But it's very good for preserving semantic translation that we are doing. And so if we look at the loop evaluation, now it's going to execute the condition until it's true. We can actually prove the judgment of loop evaluation. So the loop evaluation can be executed until as long as the condition is true. Another interesting one is for the allocation, right? So it's a two-step process. First, we are going to allocate a new empty object on the heap. So that was the store that we introduced previously. And then the value of the variable is going to be the address in where in the store that new object was allocated. But the big step semantic do not allow us to represent error case, right? If we don't have a rule for a given program, we cannot reduce it. But when we do verification, we want to have explicit error behavior. So we also implemented a functional semantic that is the option monadic form that if the result do not have error, is going to return the sum of a value. If there is such any error, it's going to return none. And if we look a little bit at the while rule, that is also one of the interesting ones, here we need to guess the number of iterations in order to execute the loop. So we have the fixed index that we have seen previously, and it's going to execute the loop 0 times, then 1 time, until we figure out that the condition becomes false or there is an error case. Therefore, we need to execute the loop until that index. So we prove that the two representations are equivalent, which means that if one of the semantic reduced to a value, the other reduced to a value which is equivalent, and the error behavior are also conserved. Now let's look at the fun language. So our fun language is a regular functional language which has some of the collective form operation to which we want to simplify the program to, such as the sum, the product, or a sequence of elements. And in order to transform from the imperative language to the functional language, we are going to encode each of the monadic operation into this functional language. So the non-value will be an object with a flag of value false, and the non-value will be an object with the flag of value valid true, and the data will be the G. And if we do a dereference, we first verify that the variable, the location is within the store, and yes, we can return the sum of the actual dereference of the store, otherwise we will return none. And we also prove Sandler's theorem that if we transform an imperative language into the functional, it is semantically preserving, and each program are going to always be reduced to sum of something or none. And of course, the value and the error are also mapping to each other. So now we are going to see how we can use that for analysis and verification. Like we said, when we transform into the fun language and it's going to be reduced to something, we just have to verify that the program can be reduced to sum of G. And to do that, it's simply verifying that the valid flag is being reduced to the value true. So there's some transformation rule that we can apply to the functional language, so they are not exhaustive, but one familiar is the one that when we have a value and we add a new value each iteration, we can transform that into a sum from 0 to that iteration. So our simplification strategy is to translate to a functional language and then simplify that functional language. However, it's an ordering issue problem. What simplification do we apply first? Do all the simplification can be applied and so on? So we need to have a heuristic or strategy base or maybe machine learning. But it's specific by nature, because in order to apply simplification, it needs to be valid for the whole program, at least the whole loop. So it's not very feasible in practice. And so we are going to transform that. And like I said, we are going to introduce speculative rewriting. So we are going to look at the first loop and do some speculation on the value of each variable in order to try to transform them into a functional language. If when we do the speculation, we encounter an error, we go back and we speculate differently. So that approach was based on a learner idea of interleaving data flow analysis and compiler optimization. And if it's valid, we can go to the next loop and so on. So we are going to illustrate that idea later. And so the kind of speculation that we can do is like when we have a scalar recurrence, we can assume that the scalar was a polynomial of a given degree, or if we detect that a value is assigned to a loop index, at each index we can detect an array creation and so on. So let's take a much simpler example that we had before, and the same thing, we want to transform to the Fen language. So now our first speculation is going to say all value are constant, because we want to approximate the scalar by a polynomial. And so we assume that at I-1 we have all value 0, 0, n, and so at index I it's going to still stay 0, 0, n. But when we execute the program, we realize that, well, the value j actually become 1. So here we have, at index 0, we have a value of 1, and we have an error between what we expected and what we had of 1. So we are going to speculate that actually j is a polynomial of degree 1 that give us 1 at 0. And we can do another, so we go back and we redo the iterative process. And here we realize that now the sum is actually not constant. And now instead of a difference of 1, we have a difference of I. So we speculate a polynomial of degree 2. And now we actually have the three variables actually follow our speculation. And similarly that we saw before, now we need to know how many times the loop has been actually executed, and here we can speculate that it's k and transform have the value of j and sum at the end of our loop. So let's take a look at the evaluation. So we implemented Sigma, a small prototype to handle a subset of the C language, and we evaluate it against C-horn and CPA checker on some benchmark of the SVComp. It's a competition for verification. So here is a small example of such program that we can verify. I don't have much time to talk about it, but there is some non-deterministic, which is an interesting modelization that the non-deterministic aspect has been modelized by the random function that for a given point in the program, like we have for each point, we can have for each point in the program, we have a spatial temporal unique representation for each statement. We can say that we can differentiate between the random value at index 0 in the loop, or at iteration 0 in the loop, or iteration 5, for example. So round of P2 of 1 will be different of round of P2 of 3. And here we see that A and B have been transformed into the sum of some if function. So we run our tool on different few benchmark, and we see that we are in par with CPA checker and C-horn in terms of performance. So we are as performant as C-horn, and we are little bit more precise, so there is no false positive. And so here are a little bit shorter. So C-horn, when it's red, it detects it's a false positive, whereas we don't have any false positive, and the timing is similar. So to summarize, we are verifying program with loop and dynamic allocation by translating a low-level imperative language into a functional language by a semantic transformation, semantic preserving transformation, and we are applying a rewriting in order to simplify the program. Thank you.
All right, questions while the next speaker sets up. Any question over there?
So thank you for the talk. How long does it take to do these analyses exactly?
So it takes a few milliseconds. Okay. So because we have some timeout. For example, like for each loop, we do a speculation, and if there is a problem, we have to backtrack and do another thing. So if some of the program that we analyze had like 3 or 4 nested loop, so here it can start to be exponential. But in most of the program, it takes a few hundred milliseconds.
Okay, and if you have a large program that has like a lot of loops, it will quickly add up.
As long as it's not nested.
Yes, but if it is nested, then
yes.
But because that's typically not that high.
So the thing is, like you need to speculate for the first loop, then you need to analyze the inner loop with the first speculation of the first loop. So if your speculation is incorrect at the first time, then all the work that you do in the inner loop will have to be redo for the next speculation. So it can take a bit of time.
All right. Thank you, Gregory.
Thank you.